Hello everyone. We're going to talk about simple linear regression model in this lecture. So particularly we're going to focus on the following 5 points. The first one is the nature of this simple linear regression model. Second, we're going to talk about how to estimate parameters of the simple linear regression model. Then we're going to talk about 3 key assumptions that ensure that the least squares estimators are good estimators. When we say good estimators, we mean unbiasedness, consistency, and efficiency, obviously. Right? Then we're going to talk about the consequences of the violation of those assumptions, and the 5th point is going to elaborate on the simulations which help us to get the empirical sampling distributions for least squares estimators. Now, for these things we need 2 important R packages. One of them is called AER, that stands for Applied Econometrics with R. Okay, this library is basically accompanying that book, Applied Econometrics with R. Then we have Mass Library. So these 2 guys are important. Okay. Now let's start with a motivating example. Let's suppose that the student performance is in any class or in any school is a perfect linear function of the student to teacher ratio. Okay, in each class we have, let's think of schools. Okay, I stands for school. So we say that the test score, the average test score at school I is a perfect linear relation, is in a perfect relationship with the student to teacher ratio. So the number of students divided by the number of teachers. Obviously this line is going to be downward sloping, some kind of line like this, and its intercept is 713, so it's going to pass from that point. Maybe I have to do it, I have to use a different color. So it's going to be something like this. So 713 is going to be here, given you put scores on the y-axis and SDR on the x-axis. Okay, so why is that? The reason is that our expectation tells us that the more students you have in a class, the worse is going to be the performance of students in that class. You see, so that is the hypothesis. That is the hypothetical relationship, which is perfectly linear. You see, 713, that is the intercept, and -3 is the slope. Right, now let's see what happens. Suppose we have a sample data. We create 2 vectors. One is for STR and the second for test scores. You see, that is the way to create vectors in R. You basically put C and then the values, you close the parentheses, and that's all. That is the way to create vectors. Anyway, let's move on. So here we have the R code to plot everything. Here we make scatter plot. How do you make scatter plot in R? So the variable that you want to put on the y-axis comes first, and then you use tilde sign, and then the variable that you want to put on x-axis comes second, and these guys are actually default. These guys are actually optional things. If you want to change the y label, you have to add the label for y. PCH20 stands for the field dots, for the scatter plot. And by the way, this AB line that gives you, the line that is plot of a line with intercept 713 and with slope equal to -3. Okay, and what we see here, we see that the relationship actually is not perfectly linear, because the data points are not actually located on this perfect line. So something is wrong. Our hypothetical relationship, linear relationship, does not really hold. Okay, so what is going on here? Let's talk about that. So we find that the lines, the data points, they do not touch the line, and although our claim was that the relationship is perfectly linear, relationship between STR and student performance is kind of perfectly linear. So why is that? Why do we have deviations from the perfect line? I mean, that might be due to, for example, randomness, or maybe the relationship is not bivariate at all. Maybe there are some other influences that we overlooked, right? For example, background of students may play a role in their performances. Those are basically additional influences that we did not account for. Okay, those guys, randomness, additional influences, these are actually accounting for this difference between the observed data and the systematic relationship that we hypothesized. We hypothesized the systematic linear relationship, but it turned out that the real data is not that linear. Actually, we have this downward trend. Overall trend is downward, but there is no perfect systematic relationship, and we assume that is due to randomness of the data, randomness of the sampling, and randomness of the data generating process, actually, additional influences maybe, and to account for these things, for these factors, we actually change our linear model a little bit by adding the so-called error term U. Okay, so everything that we could not account for, they will go under the error term U. Okay, so U accounts for all the differences between the regression line and the actual observed data. So these deviations, there are other sources of these deviations. They may be due to measurement errors, as we have mentioned already, leaving out some important factors that are relevant in explaining the dependent variable, and so on and so forth. In the end, you see, our motivating problem helped us to, correct the hypothesized model and add this term U. Okay, so UI, maybe I have to add I's here. So UI is actually the addition that helps us to save this model. Okay, so it is basically user accounting for these differences between the data and the systematic linear relationship. Anyway, so we have terminology for the regression model with a single regressor. We call it simple linear regression model, obviously. And in further classes, we're going to talk about multivariate regression model, or multiple linear regression model, where we have one variable explained by several other variables. Okay, so the variable that we want to explain is usually put on the left side of the equation. On the right side, we have beta 0 intercept parameter, beta 1 slope parameter, xi is called regressor or right side variable, and ui is the error term. And by the way, y has several names: dependent variable, regression, or simply the left-hand variable. Independent variable, xi is called independent variable, regressor, or simply the right-hand side variable. Okay, we have talked about these things. Let's move on. Now let's talk about the estimation process of coefficients in the linear model. Okay, so overall we're going to follow this routine. First, we are going to introduce the Canadian schools dataset from AER package. So this dataset includes information about the characteristics of schools, like number of teachers, number of students, location, district number, the scores of students in different exams. Okay, and then by using this dataset, we're going to create 2 new variables. One of them is called student to teacher ratio, STR, and the second one is score. And then we're going to compute descriptive statistics for these 2 guys, for the STR and score variables, and we're going to make a scatter plot for them. Okay, up to this point, you see here, we're dealing with some random data. At this point, we dealt with the random data, but now we are going to work with a real data, which is a random sample from Canadian schools. Okay, so that is the difference here. The STR in this example, in the context of the Canadian schools, they are actually going to be computed from the real data, not from arbitrary sample. Okay, so what is STR? STR, we're going to define STR as the number of students divided by the number of teachers in each school of Canada that we have sampled. Score is the mean of average mathematics and reading scores. So basically we add up average mathematics and average reading scores at each school, okay, and then divide by 2. That gives us the score variable. Clear? Yeah, and then we proceed in this way. We estimate the model parameters using this data. So we have the 2 important variables, STR and score. We use STR to explain the score variable, the student performance. Yeah? Score is kind of measurement of some kind of measurement of the student performance. So we have 2 ways. One is brute force method, and the second is using the built-in functions in AER library. Now let's move on. So here is the R code. First we start by attaching the library AER basically attaches the important library. If you don't have this library, you have to use install packages AER. Okay, that is the command that you have to run so that this call could work properly. So if the call doesn't work properly, it means that you have not installed this package. So make sure that you have this AER package installed in your local computer. And then after we have called this AER library, we can basically attach this dataset, Canadian schools dataset, and then we can basically create 2 new variables. So to create 2 new variables within the K-schools data frame, you have to use the $sign. So $str is going to be equal to number of students divided by number of teachers. Okay, the same goes for score variable. So we create a new variable called score by using the $sign, and $sign is going to be equal to, the score variable is going to be equal to the average of reading and mathematics score at each school. Okay, after we do that, we want to show the descriptive statistics for these 2 important variables, because we are basically these two variables are the variables of interest for us. One is dependent variable and the other one is independent variable. So that is how we have to start econometric analysis or statistical analysis. We have to describe the data, have a look at descriptive statistics and see what is going on there. That is the starting point all the time. Okay, so the way to calculate the average is use mean of STR. So dollar sign is basically, you can think of a dollar sign as a key for this data frame. Data frame is a container, so to open the container you have to use dollar sign. Okay, and the same goes for Canadian schools score variable. And then we calculate standard deviation by using ST function. ST returns the standard deviation of the designated variable. Okay, and then we want to calculate 10%, 10th, 25th, 40th, 50th, 60th, 75th, and 90th% quantile. So what do we mean by like 10th percentile, for example? I mean, percentile is basically dividing the data set into 100 equal parts, and for example, 10th percentile means dividing the data set into 100 equal parts and choosing the value which has 10% of the whole data set less than or equal to itself. Okay, that is the value. So suppose this is the data set, okay, the distribution histogram of the data set, and the 10% of the 10th percentile, so basically corresponds to the value which has 10% data to the left of it, or 90% data to the right of it. Okay. Anyway, so we calculate the quantiles using the quantile function for both STR and score variable, and then we put everything on the, we put everything into the container by using data frame function. Data frame, so average is basically is a vector. So the first column of the data frame is average, and that is basically a vector. The second column is standard deviation. Again, this is a vector of standard deviations, first for STR and second score. And quantile is basically, you see, when you say R bind, that stands for row bind. So basically you put two row vectors together, right? So you have like 10th percent quantile, 25th percent quantile, and so on and so forth. Okay, this is for STR variable, and then the same goes for score. So let's say delta 10, let's use the same notation, gamma 10, gamma 25, and so on and so forth. Okay, so R bind, what is R bind function is doing? That is basically binding together two row vectors. So you see, this is a row vector and this is another row. So R bind is basically putting them together, like binding the rows. Okay, keep that in mind. And then you put all these columns together and put all of them into one container called data frame. Okay, you have to keep that in mind. You have to practice a little bit with data frame function. Also, what is good in R or in RStudio, once you start typing it, you get hints. If you type this command, if you start typing data frame command, you will get some hints, okay, from R, and then you can see. Also, if you have problem with understanding, you can put like a question mark data frame and run this command. You will get some more hints. Okay. Now let's have a look at this. So this is what we get as our distribution summary. So you see, so the average STR is equal to 19. Average score is equal to 654, and these are standard deviations for STR score. basically score variable is, you know, it has more variation compared to str variable. And what else we see? And we have quantiles. Okay, so we'll use this. Currently, we don't see any. I don't really see any abnormal thing here. You know, everything seems to be okay. But we're going to use this quantile, you know, distribution summary more when we deal with the multiple linear regression. That is more appropriate in that context. Okay. Anyway, so now let's make scatter plot of STR and score. The same function, you have to use plot function. So the variable on the y-axis, which is test score, the variable on the x-axis. I mean, this is arbitrary. You can choose. Usually we put the dependent variable on the y-axis and independent variable on the x-axis. And these guys here, you know, this guy is important, but these three guys, they are kind of optional. You know, that is, the main stands for this. Okay, so maybe I have to use different colors. So the main is basically making this guy. Okay, and then X lab stands for X label. Okay, that is for this guy. X label basically is for labeling X axis, and then we have Y label, which is for labeling the Y axis. So overall, we see that, you know, there is some kind of overall trend, negative. You see, negative relationship, negative trend, but that is not that linear. That is not perfectly linear, obviously. Okay. So we can see that even by calculating the correlation. So make sure that you repeat the definition of correlation. That might be in the, you know, in quiz or in the exam. Okay, correlation is basically measuring the linear relationship, linear association between two variables. And what we see here, we see that STR and score, they are actually negatively associated. They have negative linear association, although this is rather weak, but it is still non-zero. Okay, so there is negative relationship, negative linear relationship that is kind of weak, but it is not zero. So the next and most important question is how to fit the best fitting line. The idea is this: if you look at this, you know, if you look at this scatter plot, you know, there are many, potentially infinitely many lines that can pass from this data cloud. So which one is the best fitting line? So what is a unique way of defining a unique line which describes this linear relationship best? Okay, so it turns out that there is a way to get a unique best fitting line under regularity conditions, obviously, and that is by using the ordinary least squares method. So suppose the true regression model is this: yi is related to x by a linear function and plus some error term, right? And the first assumption that we make that is key is we suppose that we have IID Joes, you know, and the sample size is n, and then the purpose, the objective of the ordinary least squares method is to minimize the following loss function, the so-called loss function, which is the sum of square residuals. Okay, we are trying to choose beta 0 and beta 1 in such a way that this loss function, this sum of squared errors, are minimized. And be careful, you know that this guy is nothing but, you know, by looking at this, maybe I have to erase everything. You see, if you look at this, this is actually by definition, by definition, UI is, I mean, this function is nothing but sum of squared error terms. Okay, because UI itself, by this relationship, UI is yi minus beta 0 minus beta 1 xi. Okay, anyway, we know from calculus how to optimize and minimize a function. We take derivative with respect to beta 0 and beta 1, and we set everything, both of them equal to 0. Both of these first order conditions are set to 0. That is the way to, optimize a function. And what we get is we get two first order conditions, two linear functions in two unknowns. Okay, so that means that the solution for beta 0 and beta 1 is going to be unique because we have two linear functions in two unknowns. Okay, and I don't want to spend time on deriving this mathematically. You can find it in the internet, but I promise, if you do derive everything, you will get a function. So the formula for beta 1 is going to be in this way, and beta 0 is going to be in this way. Okay, so these are already formulas. And by the way, the hat sign here stands for the fact that we have used the sample data. Okay, that is, you have to be careful. This beta 0 and beta 1, they are describing the true relationship, the population relationship between x and y. Meanwhile, beta hat 0 and beta 1 beta hat 1 and beta hat 0, they are actually the estimates of the true parameters. So therefore we put hat to denote that those guys are actually sample estimates, actually estimators. They are functions of the sample data. Here, by the way, you have a useful widget to practice with the ordinary least squares estimators. I suggest you spend a little bit of time to play around with this thing. Okay, how to get OLS estimates using R? We mentioned that there are two ways. One way is to explicitly compute the values of estimates using R, and the second way is, this is the hard way or brute force way, and the second one is, we have a built-in R function that is called LM function, and that is easily and instantly estimating the coefficients for us. So you don't need to do it manually, but probably it is instructive to do it manually just to see what happens. By the way, if you do it manually, what you do, you basically plug for values in beta 1 and beta 0 formulas, beta hat 1 and beta hat 0 formulas. So first one is covariance of y1, yi and xi. So basically you take STR and scores cross product for each index, then sum, and then divide by the variance of STR. Okay, that is the beta 1 formula. And then beta 0 can be found by mean of y, which is score, mean of dependent variable minus beta 1 that you have already received, times the mean of STR. Okay, that is basically a formula for beta hat 0. You can see that. Okay, so just plug for values, the corresponding values in the formula, and you will receive those coefficient estimates. And in this particular example for Canadian schools, we receive intercept estimate equal to 698, and the slope estimate is minus 2.27. So still we have, with real data, we see that there is, some kind of negative relationship association between score and STR, student to teacher ratio. Okay, now let's talk about the built-in function. Instead of doing it manually as we did previously here, you see it's a lot of things, right? You have to do a lot of things here, right? Many lines of codes, but instead you can use the built-in function in R, which is this. Okay, You can call, I mean, this is the name of the object, you can call it the way you want. So LM stands for linear model, then you type score, then tilde, str, and you point to the data container where this score and str variables are living. Okay. Then after that, you basically use the summary function, so it summarizes the linear model, and in that case you get this kind of nice table, nice, you know, output. So here you get the estimate for the intercept. So this is the beta 0 hat. Okay, that is equal to 698.9, and beta 1 hat is equal to minus 2.27. I had to do it in this way. And what we see here is we have standard errors of these estimates, but we're going to talk about this later on, but maybe it is good to mention it in time. So these are standard errors of those estimators for intercept and for the slope parameter. Okay. And here we have t-values. So basically you are the output that you see is readily reports the p-value and t-value for the hypothesis test that, you know, two separate hypothesis tests about the intercept, that the true intercept is equal to 0, and the alternative is that p0 is not equal to 0. Okay, so this hypothesis test is basically rejected because you got p-value. This is the p-value column. So the first one stands for the p-value of this hypothesis, and the second hypothesis is about, obviously, is about you know, the slope parameter. H null tells you that beta 1 is equal to 0. H alternative tells you that beta 1 is not equal to 0. Okay. So the first one is about beta 0. The second one is about the beta 1. So in both cases we got very low p-value, which means that null hypothesis should be rejected. Also, you can have a look at the t-values, corresponding t-values. The t-value about the hypothesis, I mean, of the hypothesis test about beta 0 is 73.8. That is far away from positive 2. So the rule of thumb is telling you that if t-value is greater than 2 in absolute value, you have to reject the null hypothesis of equality of the parameter to 0, right? That is the null hypothesis, and that is rejected when t-value, the absolute value of t statistic, is greater than 2. The same goes for the beta 1, you know, parameter. The null hypothesis that beta 1 is equal to 0 is rejected because t-value is greater than 2 in absolute value. T statistic value is greater than 2 in absolute value, right? So both p-value and t-value approaches, critical value and p-value approaches, they should give you the same conclusion. They cannot contradict each other. Remember that. And what else we see here? We see here, like, obviously significant codes means that this is significant at different significance levels. Here, for example, this guy is if you see three stars there, it means this is, even if you choose the significance level equal to 0.1%, you would reject this hypothesis. And these other things are following. Now we have residual standard error that is equal to 18.58. Multiple R squared, that is yet another measure that we are going to talk about. Okay, that is basically evaluates how linear model fits the data. Okay, which percentage of the variation of the data is explained by the model. we're going to talk about the other animals here. So here we have F statistic. F statistic is basically, evaluating the joint hypothesis. Look here. Here we got in the first and in the second cases, in the second lines, we performed individual hypotheses about beta 0 and beta 1. Meanwhile, the F statistic is basically used in the context of the joint hypothesis about beta 0 and beta 1. Okay, joint equality of these guys to 0. Okay, beta 0 equal to beta 1, and both of them are equal to 0. Okay, this is joint hypothesis test. And alternative is that at least one is not. At least one is not. Okay, as you can see, the p-value, let's forget about F statistic for now, but we can see that p-value is very low. It's extremely close to 0, and therefore there is null hypothesis that both parameters are equal to 0 simultaneously is rejected at even 0.1% significance level. Anyway, let's move on. What we see here is that it's scatter plot with the best fit line. First, we already know this scatter plot function. We have to use plot. Then we use score and SDR, right? And then you see we also know this AB line. But if you remember previously, we used this AB line in this way. We added. Okay, let me write it in this way. In the previous slides, we used AB line in this way. We said AB line. First, I supply the intercept value 715, I believe, and beta was equal to -3. Okay, but now this linear model, it is a regression model that has already been estimated using LM function. Okay, LM score SDR. We have already, this object linear model, it has already been defined previously. You can see that. Look at it. We have already defined the linear model. We have this object, and it contains the intercept and slope parameter estimates, and therefore we just supply it to AB line, and that's all. Once you supply it to AB line, you get this nice regression line fit to the scatter plot. Okay, so what else? So after fitting a linear regression model, now a natural question is how well the model has performed, right? So this is the line that we think is the best one, and the data is given by the scatter plot. So how can we evaluate the fit of the model to the data? How can we do that? So it turns out that it's not so easy to do with eyeball analysis. Visually, it's really difficult. So we have to calculate some kind of measures. So there are two widespread measures of the so-called goodness of fit. Goodness of fit. So measures. So there are two measures of fit. One is called two widespread measures of fit. One is called R-squared, or coefficient of determination, and the second one is standard error of regression. Okay, so standard error of regression, by the way, is reported by residual standard error. Okay, that is the name of standard error of regression is a little bit changed here in the output, so you have to know that they have the same meaning. Okay. Anyway, so we have two goodness of fit measure, and they evaluate how well the model, the linear model, fits the data, okay, the model in general, because you may have nonlinear model also. So therefore, goodness of fit measures, they are measuring how well the model in question fits the data at hand. Okay, cool. Now let's talk about R square. So R square is the coefficient of determination. It is explaining, it is showing the fraction of variation in the dependent variable explained by the model. And how we do that, we define two other animals. One is called ESS, explain sum of squares. Okay, so to what extent the line is deviating from the average. Okay, so square deviation, sum of square deviations of the line from the average, and then you have total sum of squares, that is the second animal. Total sum of squares is basically very similar to the variance of y. It tells you, it gives you the measure of the square sum of square deviations of y values from its mean, and then in the end, coefficient of determination, or R squared, becomes explain sum of squares divided by total sum of squares. So basically it tells you, this is the model variation. Okay, this is data variation. You see, y hat is basically the line, the function of the line, and the TSS is the variation in the data. So R squared gives you the percentage of the variation in data explained by the model, by the variation in model. Okay, and that is straightforward. That is basically the ratio of ESS to TSS shows how much of TSS is explained by ESS. As simple as that. But keep in mind that as long as you have, maybe I have to add that, as long as you have intercept, as long as you have intercept, you have included intercept in the model, then TSS is going to be equal to ESS plus SSR. Okay, because it may happen that you instead of, for example, instead of calculating the model like this, beta 0 plus beta 1 SDR, you may opt to drop beta 0 and calculate the model without it, without the intercept. Okay, so as long as you have the intercept in the model, this equality TSS equals to ESS plus SSR equality will hold. And if you do manipulation, you know, if you basically put it back, you know, if you substitute for TSS, you will see that this is equal to, so I'm sorry, so I have to, so substitute for ESS, you can say that ESS is equal to TSS minus, you know, SSR all over TSS, and that is gonna give you this alternative formulation for the R squared, for the coefficient of determination. Okay, so then we have yet another measure of the fit, goodness of fit measure, that is called sum of square residuals, right? I'm sorry, this was not sum of square residuals, but standard error of regression that is closely related to sum of square residuals, right? Sum of SSR is basically the sum of square residuals. So U hat is called residuals, that is the error estimates. You see, whenever you have hat, U hat is called residual, but U without hat is actually error term. You have to be careful with that. Okay, so this is the second measure of fit, standard error of regression, SER, that is closely related to SSR. So SER is basically equal to SSR divided by n minus 2. yn minus 2 because here in this simple linear regression model we have two coefficients, okay, beta 0 and beta 1. If you had, for example, 5 coefficients, then you had to subtract a minus 5. Okay, be careful with that. Okay, so again, UI is residual, but UI hat is residual, UI itself is the error term that we never observe. Be careful with that. Okay, now let's have a look at this summary again, summary of the linear model. What we see here, we see, R square is in this R output, R studio output, it is called multiple R squared. Remember that. This is the same thing as R squared that we have talked about, and that is just 5%. It is quite low. It means that just 5% of variation in the dependent variable is explained by the model, okay, by the linear model. And then standard error of regression is 18. Okay, the disadvantage of standard error of regression as a measure of the fit to R square is that this is unbounded. So standard error of regression can be anything from 0 to positive infinity, but R square is bounded both from below and above, so this is always between 0 and 1, given you include intercept to the model. Okay, therefore R square is much more useful, more widespread measure of fit in econometric analysis. Okay, now let's move on. So here we show how you can calculate standard error of regression manually, but that is not really important because the summary method reports the standard error of regression in a ready way, so you don't have to do this many manual calculations. Okay, somebody has already done it and wrote a ready function for you. Okay, now we have talked about the measures of fit. We have talked about how to get OLS estimators. We already know how to get the OLS estimators mathematically, right? Let me repeat it. Like mathematically, the best fitting line is found by taking the derivative of the loss function, sum of square residuals, right? Sum of square errors actually. So we minimize the sum of square errors, and that gives us the mathematical formulas for the OLS estimators. That is easy. We have talked about that, and then we have learned how to perform that, in R. So mathematical things are obviously nice. We have to know the mathematics behind calculations, but in real life applications we have to use calculators, because we cannot do things manually all the time, right? So this ln function is actually the function that is needed for us, that is basically gets the OLS estimators and evaluates them at the sample data. Actually the ln function gives us the estimates for intercept and slope for all linear model parameters actually. And then we talked about mathematics of this best fitting line. We talked how to calculate it in R. Now we also talked about how to compare, how to assess the fit of the model to the data, and we talked about two measures of fit. One is R square and the second is standard error of regression, and we said that R square is much better in the sense that it is bounded from both from above and below, so it is easy to compare models using R square, or coefficient of determination, in other words. Yeah, you know, that is the other way, that is the other name of R square. Okay, and by the way, we learned that the standard regression output in R programming reports R square as under the name multiple R square. Okay, now the next step is to evaluate the conditions under which OLS estimates that we receive, you know, the line parameters, the OLS estimates that we receive, they are actually good estimators. They are actually unbiased, consistent, and efficient. In class we talked about unbiasedness and consistency. Now probably we have to close that topic by talking about the asymptotic distribution of the estimators, OLS estimators. You know, how we can, under which conditions we can apply central limit theorem. So it turns out that there are three important conditions that are guaranteeing that OLS estimators are normally distributed asymptotically. So CLT, central limit theorem, applies. The first one is the conditional expectation of errors conditional on x is equal to 0. Second one is the data is IID. You know, the sample data is based on simple random sampling, in other words. And third assumption is large outliers are unlikely. So x and y, they have non-zero finite kurtosis. The kurtosis, by the way, this is kurtosis. That is basically the measure of the tails of the distribution. You have to keep that in mind. Kurtosis. Sometimes this is called fourth moment of the distribution. Fourth moment. Okay, anyway. Now let's talk about assumption 1. Assumption makes sure that there is no any systematic pattern in errors, because suppose you have systematic pattern in errors. As you know, x's increase, you see u becomes, errors also get larger, so that means that your model is actually not correct, isn't it? You know, the errors, you know, there should not be patterning errors, isn't it? I mean, if a person makes the same error over and over, if there is a pattern in his errors, that means that he's stupid, right? The same goes for the model. If the model makes errors that can be predicted, that follows some kind of systematic pattern, that means that the model is not correct. So this first assumption is really important. That makes sure that the OLS estimators, they are, you know, all these unbiasedness, consistency issues, they are really attached to this first assumption, mostly attached to this first assumption, because you know, that is one of the most important parts for consistency and unbiasedness of estimators. Now, how do we show it by simulations? We are generating data based on quadratic model. So this is the true model, suppose. Here, by the way, it should be I, lowercase I. So the model, the true data is generated by a quadratic model, and we feed both linear and quadratic models to the data. Obviously, the linear model is a false model that we impose, but quadratic model is the correct model. and let's see what happens. I mean, let's see whether assumption 1 is violated in both of these cases. Let's see. So here we're going to use this for our functions, our uniform, our norm, predict, and lines. I mean, our uniform and our norm, they are known functions. They are helping us to draw random numbers from uniform and normal distributions respectively, whereas lines is basically adding a line segment to an existing plot. Okay, and then we have predict. So after you get this linear model, for example, suppose you have linear model, let me call it mod. You can call it anything that you want. The objects can be named the way you want. You can call it apple, peach, banana. So let's call it mod. So suppose you have mod model, which is linear model of y, x, and data is, for example, say dot, right? After you do that, you can use predict. Predict lm, predict mod, and then you are going to receive that is going to give you, if you use this predict mod function, that is going to give you the estimate y hat for the line, the predictions on the line. Okay, y hat is going to be, the values on the line are going to be obtained by using this predict function. Okay, now let's have a look at this data set, not data set, but our code chunk. First, we are going to set a seed for reproducibility, so you can reproduce the results. If you set the seed of the random number generated to 321, we suppose we have x is uniform between -5 and 5, and we draw 50 such random numbers from uniform distribution, and the errors, they are normal, so the mean is 0, the standard deviation is 1, and we draw 50 such values from normal distribution. And by the way, you see we did not specify the mean because the R norm has default values. Default value for the mean of our norm function is equal to 0. Now suppose the true relationship is equal to x squared plus 2x plus u. So once you have x and u values, you can receive y's, and then you have this, you basically estimate a simple model, linear model, and this is the false model, obviously, and then you do it for the correct model. By the way, I have to mention that when you are including the squared or exponential terms within the lm function, you see the lm function does not recognize this x squared. You see, you have to write I to instruct this lm function to see it as the x squared, not as some kind of string or some kind of expression. Okay, so you have the correct way to include x squared term or exponential term within the lm function is using by using I parenthesis x to the exponent 2, 3, 4, doesn't matter. Anyways, then we use prediction. You see, predict function takes the model as an argument, and then you say that put it I'm sorry, it has two arguments. I forgot to mention that. First argument is the model, the second argument is the x values for which you want to get the y predictions. Okay, you basically supply x values, and this predict function gives you the model's predictions for the supplied x values. Okay, so you do the same. This is plot function. It's very simple. That plots the You see scatter plot. This is adding line. Okay, yet another line. And let's see what happens, which kind of graph do we receive. So you see, this is the blue one is the linear model, and that is obviously stupid. Why is that? Because as you can see, once you go to the right of 3, the deviations from maybe I should say, just a second. So once you go to the right of approximately 3, the deviations from line, they're all positive. So obviously there is some pattern, right? Because all errors, all residuals are going to be positive. And the same goes for the values less than -2. You see here, the deviations of data points from the line, they're all positive. Meanwhile, in the middle region, you can see that the deviations from the line, deviations of the data points from the line, they're all negative. So there is some kind of pattern here. And obviously this model cannot be the true model. And obviously the expectation of UI given xi assumption is violated here. So what does this mean? This means that you fix x. So the essence is that you can fix x at any value that you want. For example, here at 4.2, and then you take the average of average of errors, and the average of errors should be 0. But that is not the case. You see, once you take x greater than 3, any value of x that is greater than 3, and find the average of errors, they are not going to be equal to 0. You see? So there is obviously a pattern between, xi and ui. Therefore, this model is false. So the assumption 1 is violated. The model is stupid. But you don't see the same for the quadratic model, because the quadratic model is the true model. That is, the data is actually generated by the quadratic model, and therefore once you feed this red model, quadratic model, to the data, you don't see that pattern. Sometimes the errors are positive, sometimes negative. You see, they're kind of fluctuating around this red line, and therefore that is a correct model. Okay, so that is the essence of the first assumption. If you are making systematic errors, it means that you're stupid, right? So if the model makes systematic errors, it means that the model is not correct. Okay, let's move on. Here we have second assumption. Second assumption tells you that the data xi and yi, they should be IID, they should be randomly sampled for all I equals 1 to n. So all data points should be sampled based on the simple random sampling. So basically, the likelihood of all observations to be in your sample are the same. So all elements of the population are equally likely to show up in your sample. Okay, all elements of the population are equally likely to show up in the sample, in your sample, for example. And if that is the case, then you have simple random sampling scheme, or in other words, you have IID assumption satisfied. Here we have some R simulation where this assumption is basically violated. What you see here, that is basically time series data. You see, in time series, for example, suppose you think of the GDP of countries. Obviously, if the country is not doing well this year, most probably it will not do well in the next year. Okay, so there is an obvious pattern, some kind of persistence in the economic growth and GDP of the countries. And that is basically telling you that there is dependence. Okay, IID assumption is violated. Or think of another example that is given in the book. So there is structural shifts in the economy, and the company wants to cope with the changes in the economy, and it starts to fire its employees, right? Obviously, this, dismissals, they will follow some kind of pattern over time. Okay, that is where the independence assumption is actually, mainly the independence assumption is violated. Okay, and in time series case, in time series data, independence is actually, there is no independence most of the time. See, here we see some kind of pattern over time. You can have a look at this simulation. And the third assumption finally tells you that large outliers are unlikely. What does this mean? Basic idea is that we don't have outliers in the data. That is the simple explanation of this. There is no outliers in the data. Why do we need it? Keep in mind that OLS is pretty like the mean estimator. You see, you remember the mean. We know that the mean is very sensitive to outliers, and OLS is also is actually a mean. It's a conditional mean estimator. Okay, if you look at the formula, it is based on sums, right? So OLS as the mean itself is very sensitive to outliers, and therefore, whenever outliers are present, they can distort your estimates to a large extent. So therefore, it is instructive that you, before doing any analysis, before fitting linear regression model, you basically analyze the data. If you have outliers, then drop them, and after that, you see fit the linear regression model, because OLS as an estimator, OLS estimators, they are very sensitive to outliers. Okay, and the simulation about assumption 3. So the idea is very simple. You are generating random data. Okay, so the true model is you see y and x, they are related to each other, but you add an outlier to y. You see, y itself is normal with mean 10 and with mean 200 and with variance 2500, but at some point you add a very big value, a very large value to y sequence. That is actually you change the 9th value in y vector, make it equal to 2000, and after you do that, you see we fit the model with the outlier with 2000. Here we fit the model without outlier. When you say y minus 9, it means the 9th element of the vector y is going to be dropped. So all elements but 9th element. So all elements will be there, but not the 9th element. The same goes for x. So here we drop the outlier, which is located on the 9th element of y vector. So what you're going to see is once you drop the outlier, the model will differ a lot. This is the picture. You see, this is the model. The red line is the model, and the blue line has has an outlier here, and the red line is basically estimated without using that outlier. That is, you see, here we have the red line is basically downward sloping line, it has negative slope, so beta 1 is basically less than 0, but here once you add the outlier you get some beta 1 greater than 0. Okay, so maybe I have to use red color for this. Okay, so beta 1 for red line is less than 0. Meanwhile, once you add it became positive, and the same goes for the intercept. You see, so we conclude that OLS estimators, like the mean estimator, they are very sensitive to outliers, and we have to be careful. And it doesn't really matter what is the source of outliers, whether it is measurement error, some misreport. You have to identify them if you want to do linear regression. If you want to perform linear regression analysis, it is better to analyze the data, identify the outliers, drop them, or at least to see their effect, you basically run the regression with and without outliers, as we did in this experiment. Okay, and see how the line is changing, how the estimators are changing. Okay, now we have to talk about sampling distribution of OLS estimators, but I don't want to dive deep into these things. They are a little bit mathematical. I'm sufficing by telling you that the CLT is going to apply to OLS estimators. So OLS estimators are going to be normally distributed asymptotically as n goes to infinity if the assumptions that we talked about hold in reality. Okay, if the expectation of errors are 0, conditional on x are 0, if the if x and y are IID, so based on if they are based on simple random sampling, and the third assumption is that there are no outliers in the data. If those guys hold, then you have beta 1 hat asymptotically normally distributed with mean equal to 2 beta 1 and with variance equal to variance beta 1 hat. And the formula for this is this. Okay, so I'll not talk too much about these things at this point, and also I did not include the simulations about sampling distributions. Probably we'll talk about them later on. Okay, now I want to conclude. So we learned how to estimate linear relationship between two variables. We use OLS. We know the mathematical background of OLS. Basically, we minimize the sum of squared residuals, sum of squared errors to get the OLS estimators, and then that is mathematical background. So we know we start with mathematical background, then we move to R implementation. We know that there is LM function, which is very useful to implement linear regression analysis. And once you fit the best fit line to data, we talked about how to assess the fit of the model to the data. So we discussed measures of fit, sometimes referred to as goodness of fit measures. They are basically R squared and standard error of regression, these two guys. And then we talked about 3 key assumptions under which we are going to have normally distributed estimators, actually unbiased and consistent, and normally distributed estimators, OLS estimators. And those assumptions turn out to be these things. First, we say that the conditional expectation, the expectation of error terms conditional on x's are equal to 0. So the expectation of errors conditional conditional on x is equal to 0. Second assumption is that you have IID sample of xi and yi. Okay, and the third assumption was no outliers, because the OLS estimators, they are very sensitive to outliers, so we want to make sure that there is no outlier, or alternatively, in mathematical lexicon, you can say that you have finite fourth moment of the data, or the variables actually. Okay, so as you have these three assumptions satisfied, then you are going to have unbiased, consistent, and normally distributed estimators, OLS estimators. Okay, so that is the conclusion of chapter 4, and see you in next classes.